Okay, so we can start. Last lecture, we introduced the concept of conjugation. And so-called adjoint representation, and also its derived small adjoint representation. This is representation of Lie group. This is derived representation of Lie algebra. And it started with a very general commutative diagram that whenever we have a homomorphism of two Lie groups, we can automatically fill this picture, with H to this so-called commutative diagram, and it introduces this important mapping. So we can derive from homomorphism of Lie groups, we can derive homomorphism of corresponding Lie algebras of these two groups. And it started, just to remind you that it started from the observation, very simple observation, that if we have a homomorphism of Lie groups, then we have here AT e to T some C, one parameter subgroup, which starts from 1, and F map it to some curve, which also starts from 1 because F preserves a unit element. And this will be some, say, BT. And it turns out by very simple computation that it is, again, one parameter subgroup. That means it should also have this form with some element from Lie algebra of this group. And we call this mapping that this new element is called F primed of this old element. Yes? And for T equal 1, we have this diagram. Then we defined what is a representation. Representation is map, homomorphism, usually called rho, to a very specific Lie group, a group of automorphisms of linear space, which is GLV. And because this is also a homomorphism, we can write from that diagram the second line. We discussed that the Lie algebra of the Lie group GLV, or automorphism of V, is Lie algebra of endomorphisms of V that are all linear mappings from V to V. So by this diagram, again, this map is defined. We also discussed how to compute it easily. It can be computed right from the diagram, but the practical way how to compute is this formula that, that you should map an element near unit element, and you always obtain something of this form. And here comes F primed of C. So this is defined by this practical formula. So also here, for representation, is just the particular case that you should map an element of the Lie group, which is close to unit element, and you obtain a unit element of this group, which is unit operator plus epsilon rho primed of C. Again, this is defined by this formula from known rho. And it is called derived representation. This is representation of Lie group, and this derived representation is a representation of the corresponding Lie algebra. So it has the properties that it preserves all structure of the algebra. First, it is linear. And second, it preserves a commutator, Lie bracket. And because this commutator, which is mapped, is already in this Lie algebra, here the commutator is given by the standard formula as we know it, usual one. So it is, of course, rho primed x, rho primed y, but here this is not some abstract formula, but it is a very concrete formula from this concrete Lie algebra. And we also, so it is something about representation, derived representation. Now conjugation. Conjugation is a map from G to G. K goes GK G2 minus 1. And it turns out it has a lot of nice properties, and also it has a nice interpretation, which we omit here, but it will be given several weeks later. But what is important now for us, that this is a homomorphism. It is more than homomorphism. It is isomorphism or even automorphism of Lie groups. But for us, it's important that it is homomorphism. That means that diagram once again can be used. So here we can feel the complete picture. This is derived homomorphism of this homomorphism. This is derived homomorphism of Lie algebra, as we see. But it is some representation, actually. We discussed it last lecture, that it is a linear operator on G, on this vector space of Lie algebra. And it also reacts properly to this G. That means that I prime G1, G2 is I primed G1, I primed G2. So altogether, I primed G is some representation, and this representation is called adjoint representation of the Lie group in the linear space, which is identical to the linear space of its own Lie algebra. So putting there also some argument, or going by these two arrows and by those two arrows, we have what? E to, put some S, some C here. Then we have this arrow goes to E to C. Then IG, it is K G minus 1 or G minus 1, okay? And now it should be this adjoint of G, and then to exponential that E2 adjoint of G applied to C. And one can also add this T here, like it was derived from, first it was a T there, and we then cancel it, put it to 1. So 1 and put it back here. Now it is quite practical. Because now we see that for T equals epsilon, we get 1 plus epsilon C G to minus 1 is 1 plus epsilon adjoint G of on C. This is for matrix groups. Yes, this formula, as it is here, is true for any Lie group, irrespective whether it is matrix or not, because this is multiplication of 3 group elements. It makes sense. But here we already added one. It is unit matrix and it is matrix C. It is not like that in general. But here we already have matrices, so we can make a product. G1, G2 minus 1 is just 1. Plus epsilon, again, G, C, G to minus 1. And of course, this guy makes no sense in abstract way, because in abstract groups and algebras, because it is a multiplication of a group element with a Lie algebra element. It is not defined. But for matrix groups, it is defined. It is just a matrix, 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 so we can do this product. Yes, but this can be done, everything also in abstract world. This product is only defined for matrix groups. So this is, in a sense, the advantage of using matrix groups, that you can do some products which are not defined abstractly, and it is then simpler. So what we see is this. So for matrix G, we have explicit formula that it is G, C, G to minus 1. Important for matrix. Now, if you compare it with conjugation, it looks very similar. Yes, it is just sandwiching of the element inside by 2 group elements. But here you have 3 group elements. It makes sense also abstractly. And here it is this forbidden product, officially forbidden, that the product of group element and Lie algebra element, it only makes sense for matrix Lie algebra. So the formula looks like conjugation, but it is not a conjugation. Yes, it is something different. And now this picture for adjoint representation, if we put adjoint representation here, here it is invertible linear operators of Lie algebra. And here is Lie algebra 2 endomorphisms of G, so all linear operators. And here should be ad primed, which we called small ad. Sorry. Now it is an easy computation, do it yourself, that we know the general formula for the primed of rho. Yes? Then this is primed of adjoint, and here you have formula for any adjoint, including this small one. Yes, so you should write just adjoint with respect to 1 plus epsilon c on some d, or I will do it here. Well, here it is 1 plus epsilon c d. Inverse element we discussed already is 1 minus epsilon c. So what I did, now I compute this element for rho equal adjoint using the formula for adjoint which is here. Yes. So here G is this guy and C is D. When this is multiplied, what we get is D inside plus epsilon, and it is CD minus DC. So we computed the left-hand side, and it should be 1 plus epsilon small adjoint of C applied on D. This applied on D. By this formula, for rho primed equal to small ad. So 1 on D is D plus epsilon adjoint of C applied on D. So we see here is the result. And it is given by CD commutator, because this is, of course, commutator in this Lie algebra. So we have two explicit and practical formulas to compute the adjoint representation of group and in the first line, and adjoint representation of Lie algebra in the second line. Now, it's funny that this result is true also abstractly. This is not possible. Abstractly, it is only for matrix group, but the commutator, which we obtain the commutator of matrices, but commutator also exists in Lie algebra. So actually, this formula is true also in Lie algebra abstractly, not only for matrix Lie algebras. Now, some notation in general and notation for these cases, that in general, the representation of Lie group gives you this operator, and this operator is an operator in V. So if in V we have some basis, we obtain matrices of this representation. Given by this formula. Yes. So there are n by n matrices when n is the dimension of the vector space. Now the derived representation also works in the same vector space. So in order to obtain this operator using the basis, we also get some matrices in the same vector space. But now, here, in the case of the derived representation, in general, this C is from Lie algebra, and Lie algebra is also a linear space. So there are two linear spaces here involved, Lie algebra and the linear space V when the representation holds. So here also we have some bases, the basis of Lie algebra. And because this is linear in C, in order to do this formula completely, it is enough to know what this operator produces when acting on the basis of the vector space V. Well, so by this formula we have, as always, but here, this is a finite set of numbers. For each I, each A, each B, you have something, some number. So in my book, it is denoted like that, some abbreviation. Yes. In contrast, here, you have no basis of Lie group or something like that. So here you should know the matrix for all Lie groups, all group elements, yes. But here, all Lie algebra elements linearly depend on some basis, yes, bases and components, as usual, in vector spaces. So instead of an infinite number of numbers here, it is enough to have some finite set of numbers. What this number, what are the interpretation? That we see here that this I is that which linear operator, and this AB that which matrix element of this operator we are speaking of, yes? So there are two kinds of indices on this object. Two indices are from the basis of the V, and one index is from the basis of Lie algebra. So these numbers somehow behave if you change bases both in V and both in Lie algebra. Now, what those general formulas say you when you apply it to this, in particular, this small ad. So now put rho primed equal adjoint representation. Yes. So rho is adjoint and rho primed is small adjoint. Sorry, I forgot to tell that these guys are called generators of representation. Representation. Usually, we mean that generators of the representation rho, but actually they are of rho primed. Yes. So if you have a representation of group, there exists something like of Lie group, that something like generators of the representation, and they are what they are. First of all, they are operators of representation of Lie algebra, but not all of them, but only Lie algebra, the basis of Lie algebra, how is represented. So this is the definition, what are generators of the representation, that find basis in Lie algebra and make representation of the basis of the Lie algebra in terms of rho primed. There are finite number, usually small finite numbers of generators, because there is a finite number of basis of Lie algebra, of course, infinite dimensional Lie algebra. So it is tautology, but we are speaking usually on finite dimensional Lie groups, which means that they are finite dimensional manifolds, and they're Lie algebras, which are finite dimensional linear spaces. So the basis is just from 1 to 2 dimension of this Lie algebra. And now, what are the, or what about the generators of these two, or of this? So we have the formula now that instead of rho primed, we write adjoint, small adjoint. Now, I already told that the argument for the exceptional case, rho, this adjoint is not written as in the bracket, but something like an index. Yes, this is particular case of this for rho equal capital Ed. And now, this is the exception that in general case, we have two different vector spaces. So these indices are of this different type. This goes from 1 to the dimension of V, and this goes from 1 to the dimension of Lie algebra. Yes? But now, these two vector spaces become one vector space because our representation is in vector space given by Lie algebra. So we represent Lie algebra in the vector space of Lie algebra. Yes? That's why these two indices are the same, of the same type. And what we get? First, we get something like that. So here should be I, here should be J, K, E, K. But at the same time, the formula is here, and we see that it is a commutator, the result. So the result is actually a commutator, EI, EJ. And a commutator gives you another set of numbers, structure constants. Yes, this is definition of structure constants of Lie algebra in given basis. So now, if we compare that for this representation, these are representation operators matrix elements from the general formula. But at the same time, it is given by the formula that this is given by a commutator. It is here or here. So we should write a commutator, explicit expression for our case of the result. But commutator gives you another set of numbers. So this set of numbers equals this set of numbers. So what do you see? That if you want to see matrices of this representation, for matrices of generators, yes, here are, these numbers are matrices or numbers connected with matrices of generators. Here is the number which generator, and here are two matrix elements of this ith generator. Here we see that this I is here. So if we see structure constants, the first index here is that which generator we have in adjoint representation, and these two numbers are matrix elements of this generator. So for example, maybe you remember that there was on the recitations for Lie algebra GA1R, I think that this was the label of this algebra. We had a basis in it 1, 0, 0, 0 and 0, 1, 0, 0. It is given by matrices 2 by 2. This was called E1, this E2. Do you remember that we did it in recitations? Somebody of you did this. Who was? Yes. Okay. So we did it, and we computed all structure constants, which is, of course, very trivial here. And the result was that this is E2, as far as I remember. What does it mean? That C1, 2, 1 is 0, because there is no E1, and C1, 2, 2 is 1, it is this one here. And all other 0 except for reversed. Reversed are minus. Yes? So here we see that there are two generators. One of them, because we have two, there are two generators, we have generators adjoint of E1 and adjoint of E2. And their matrices are 2 by 2 matrices, which are easily visible from this result, that this is also minus C2, 1, 2, and this is minus C2, 1, 1. So everything is here. What do you need? And just take this formula, fix the first number. For example, here, if we want to construct this matrix, we should fix this one. So it is here and it is here. And here, for example, it is said that in your first matrix, 1, 2 element is 0. And so on. Here, 2, 2 element is 1. So it is, here is 0, here is 1, and here is something you should compute. And what is also quite interesting is the situation for SU2 and SO3. So then we have that in some basis we obtained a result that it is like that. Do you remember that for there were some long exercises with SU2 and SO3, and we obtained for both of them this result. But we know that in general it should be ij, okay, here. So we see that in this case these structure constants are given by epsilons. Now we know that fixing this I is that which matrix, and kj are matrix elements of the adjoint representation. So fixing I here is fixing this I, and these jk are then something like matrix elements. But remember that we introduce something with the same matrices, that there are some matrices, the basis of SO3, that Lijk is minus epsilon ijk. Maybe you remember that we introduced this L1, L2, and L3 as a basis of Lie algebra SO3. And here the basis was minus I half I sigma, well, sigma j will be Ej. This I did on myself in the lecture, and this was SO3 was done in the recitations, yes? So now, if you have a look on these formulas, that by your C's, structure constants, you have already matrices of adjoint representation, and your C's are those guys, and by these formulas you have some matrices defined, so you can verify that we have the formula that this goes to Lj with respect to adjoint representation. So matrices of adjoint representations of SU2 give you basis of SO3. So we see already that SU2 and SO3 are somehow very intimately connected Lie algebras. And namely, I don't remember whether we introduced the concept of isomorphism of Lie algebras. We defined, hopefully, what is homomorphism of Lie algebras in general. If we have two Lie algebras, then some map, linear map. So what is a homomorphism? Linear maps which preserves the structure that is linear, it is 1/2, and preserved commutator. Isomorphism is what? Linear map, which preserves everything, but it is at the same time bijection. Yes? So linear isomorphism as a linear map, and then preservation of commutator. This is isomorphism. And now, we easily see from, well, if you have some basis here, because you should have linear isomorphism, you should have the same dimension. Yes? So if we have same dimension, we can now, if this is isomorphism and this is basis, we can define a basis here by F image of the basis here. So the best choice of the basis in the isomorphic Lie algebra is F image of the basis in the left, of the left Lie algebra. And now what this means for your commutation relations, if in this left Lie algebra we have some structure constants and apply F of this equation on both sides. So here F preserves commutator, so it goes here and here. But then, by definition, it is this A. So here we obtain Eij, and here F sees linear combination, it is linear, so it comes here and makes those E's. So we have Cij, and curl. So we see that if you have isomorphism of Lie algebras, and if you have a basis and use the image of the basis as the basis of the image Lie algebra, the commutation relations, so to speak, are the same. Yes, in those very, very well, carefully chosen bases. Not in each basis, but in some bases, they have the same structure constants. And you can think that you can also do it in an opposite way, that if you have two Lie algebras, and in some basis, two Lie algebras, of course, of the same dimension, and if in some basis you see that they have the same commutation relations, that means the same structure constants, you can tell that these Lie algebras are isomorphic, because they are isomorphic on the basis, so to speak, and it is linear everything. So we see from this that we already know one pair of isomorphic Lie algebras, SU2 and SO3. They are not identical. They are realized by different matrices. Here you have complex 2 by 2 matrices. Here are real 3 by 3 matrices, so they are not identical, but they are, from the point of view of Lie algebras, isomorphic. They are the same. And what is interesting, that these Lie algebras came from some Lie groups. So if Lie algebras are isomorphic, the simplest idea may be also the Lie groups are isomorphic, but it turns out that it is not the case. It is more complicated. There is something called covering, two-sheet covering, and we will come to this complication maybe at the end of the semester. Yes, that there is this Lie group with capital SU. It covers by two-sheet covering, so to speak, this Lie group, SO3. So groups are not isomorphic, but their Lie algebras are isomorphic. It is strange, but we will understand this phenomenon, that how it is possible, when we understand what is this covering. Okay, so I think that maybe I didn't forget anything important from conjugation, adjoint, and small adjoint. We have formulas. We can if something is left, it can be done on recitations. I will have a look on some exercises, and on recitations we will do the technicalities. But what is important really that we have explicit formulas for matrix groups, how to compute it, and we know a lot of properties. So now we go to some next step in the theory of representations, and we introduce something which is called reducible and irreducible representations of Lie algebra and Lie group. So, representation is a homomorphism, as we know, to some vector, to automorphisms, homomorphism from Lie group to Lie group of automorphisms of some vector space. Yes. Now, in this vector space, we can find some subspace. And if we apply the operator of some associated with some element on W, which is from this subspace, in general, there is no reason that this vector is still in the subspace. This is some operator acting on the vector on subspace. The result can be outside the subspace in the vector space V, yes, in general. Yes, but sometimes it happens that this is from the subspace still. And important case is when this is for all G and all W. So for any vector from the subspace and any group element, if this guy is still in the subspace, it is a very interesting situation. It is usually called by capital letters which means that this holds for any G and W. That if you take any group element and act on any small w from big W, you have something again from the subspace. Yes? It is exceptional case. It is not the rule. It is exception. What then we can do if we find something like that? We can make something which is called restriction of rho to this V, to this W. Our rho acts on bigger vector space, on V. But if this holds, we can restrict our representation to W. What does it mean? That we will never act on vectors which are outside W but inside V. Yes? Symbolically, not very okay, but something like that. In general, this goes out by our representation, but sometimes it doesn't go out. And if it doesn't go out, we can forget about the rest. We can apply only our operators on the vectors of W. It cannot be done if some vectors go out. Yes, we cannot restrict our operators to W because the result is outside in general. Yes, but if the result is still there, we can do this restriction, which ideologically simply means that you never act by your operator on the vectors which are outside. So, and of course, you still have all properties of rho, that it is a representation, namely, with all definition properties. What does it mean? That this is, again, a representation which is smaller, like the original one. So if this is possible, you can you can find a smaller representation out of some bigger representation. Restriction on the subspace. Now, the nomenclature of what is a subspace in linear algebra also admits two special cases, that everything is subspace and zero element is a subspace. They are called trivial subspaces. Yes, that the whole vector space and it is the biggest subspace, largest, and the smallest subspace is just element zero, nothing more. So if our subspace is one of these trivial cases, it is not very interesting because it always happens, of course. But what is interesting, if we have something in the middle, not zero, not complete, but something which is non-trivial, and if we can find in the vector space V of our representation such non-trivial subspace, then it is called reducible representation. Reducible representation is there is a non-trivial vector space which is invariant. It is called that it is invariant vector space or invariant subspace. So, really interesting invariant subspaces are non-trivial invariant subspaces, not this all and zero. Yes, they are always there. If you have invariant subspace, it is called reducible. Why? Because it can be reduced to this reduction of rho to W. Now, have a look to matrices. Let's have a look. If we have a subspace, it is a good idea to it is inside, yes. Subspace is a part of the vector space. So we can choose a basis of this big vector space, which is adapted of the existence of the subspace, in the sense that all vectors we will denote by, say, EA and E alpha all together. Altogether, it is a basis of complete vector space, but this will be a basis of the subspace. And this E alpha are just added in order that we should have a basis of the complete vector space. This is arbitrary addition of linearly independent vectors in order that this is as a whole basis. It always can be done, as we know from linear algebra, that whenever you have system of linear independent vectors, you can add other linearly independent vectors which altogether form basis. There is a theorem like that. So this is called adapted basis. To W inside V. Yes, this is a structure inside the vector space. Now, if we have this situation that this subspace is invariant, or first, how it looks like when you act on these two matrices. In general, first. Action of rho G operator gives you a matrix, and this matrix is given from the action of this altogether, all the basis elements by well-known formula that A to E I is Ij Ej. Yes. So we want to do something like that, but for a basis which is divided to something like 2 halves. So here we have matrix element A, B, E, B plus A alpha, E alpha, and here the same alpha, A plus alpha beta E beta. The complete matrix now has some 4 blocks, naturally. Here is this BA block, alpha A block, A alpha, and beta alpha. And now what happens, this up to now, we didn't use at all the structure of adapted basis. It is for any basis divided to 2 halves. Yes? If you divide your basis to 2 parts, not 2 halves, by how many they are, but just some 2 parts, you divide all matrices to some 4 blocks. Yes? Naturally. Now, what happens if it is adapted basis? Do you see what particular situation holds if our basis is adapted now, and this is invariant subspace? This one, or which one you mean?
I think that one.
Yes. So, which one? This part is inside W, and if we act on vectors from W, we should still remain in W. So, yes, this should be 0 out, because this is linear combination of the vectors outside, and it should be not there. And here we do not know. Yes. So what does it mean? That which it seems to here that this should be 0. Maybe in some different notation you will have here 0. It is not very important, but what really happens that in your block structure of your matrices, of all elements, they are, for all elements G, you have matrices, and for all elements G, your matrices have one block which is 0. So, if you study your representation on the level of matrices, not abstract vectors and so on, if you see that your matrices have this structure, it is from the other side, you can see that there is an invariant subspace because of the 0 part. And you should be able to identify vectors from this invariant subspace, from the 0. We can make something like small computation, but actually we will not compute too much, to see some example, not of these matrices, but on the concept, general concept that reducible or irreducible. What is irreducible? That it is not reducible. Irreducible means that you cannot find such a vector subspace. I stress that it should be non-trivial. Trivial, of course, they are, but non-trivial. So, example, our representation will be of this type, that just leave your matrix alone as it is, but reinterpret it, that now the matrix serves as a linear operator. I introduced it last time, and our G will be SO2. So, A elements, we know that they are cosine alpha, sine alpha, minus sine alpha, cosine alpha. And now we use them as matrices, which are operators. So, this matrix act on xy, and we get x primed, y primed. So this is our representation. It is two-dimensional representation in R2 given by the matrices themselves as they are. Now we want to study, is this representation reducible or irreducible? So first of all, how what are possible subspaces of this R2? This is all R2, 0 element. So there is a single two-dimensional subspace. It is V itself. There is a single zero-dimensional subspace. This is the 0. And what the rest? All other subspaces should be one-dimensional. Yes. And how a one-dimensional subspace look like? Here is XY. One-dimensional subspace is something like that. It crosses 0. Yes, that any vector of this type, and also this is other vector, and here is vector, here is vector. So this is one-dimensional subspace. So except for trivial subspaces, the only non-trivial subspaces look like that. Now, is it possible to find one-dimensional subspace which is invariant with respect to our representation? What does this on this picture? If we have some vector like that one, yes, xy. Now we apply this matrix, general, what we get from this vector. In the picture, you should describe it in layman terms. It is rotated. Yes, it is somewhere here, and here is alpha. Yes. So what we see, is it possible that there is one-dimensional invariant subspace here, invariant with respect to the whole group? The answer is yes, clearly no, because each vector rotates, and this subspace is another subspace. It is not in the original subspace. Each subspace is given by its direction, so to speak. And with rotations, the direction changes. So we see that from this picture that you cannot have invariant one-dimensional subspace. That means you cannot have invariant non-trivial subspaces, because all non-trivial subspaces are one-dimensional here. So this representation is irreducible. There are some techniques to compute whether your representation are reducible, irreducible, and not, but here no techniques is needed. It is so simple from pictures that without any computation, just realizing what happens, you can see whether it is irreducible or not. So it is two-dimensional irreducible representation. And what happens sometime is that you find some invariant subspace, okay, but there are still vectors outside this subspace, but maybe there is another invariant subspace. So this is invariant, and sometimes it happens that you have another invariant such which is complementary to this subspace, which means that these subspaces together give you the whole space. So whenever you have a vector, you can uniquely decompose it to two parts, a sum of two parts. The first is from here and the second is from here. This is the complementary subspace. So it is not a problem to find complementary subspace to a given subspace. There are infinite number of complementary subspaces. But what is much harder and maybe doesn't exist, that if this is invariant, you should have invariant complementary. Yes? It is not clear that whether it exists. And in general, it does not exist. Even in situation when you have invariant subspace, sometimes it is not possible to find complementary invariant subspace. Very easy example, once again, is from one representation which is only mentioned in the footnote in my book, so just 2 lines, that First of all, you study group of such matrices. If you multiply two such matrices, you will obtain again matrix of the same type with this result. What does it mean? That if you take A from R plus, A is from R plus, that means real numbers with respect to addition. These matrices are isomorphic to this group R plus. Yes, the multiplication is the same. So we can interpret those matrices as a representation of R plus in R2. They are 2 by 2 matrices, so they are operators in R2. And this is a group isomorphic to R plus. So, and it is a homomorphism. Yes, check. So it is a two-dimensional representation of the group R plus. Now we want to find all invariant, non-trivial invariant subspaces again. Because it is again in R2, non-trivial subspaces are just one-dimensional. So we have again x and y. We have some vector here. Now what is the action of this representation on this vector? So we compute and then draw a picture. Here is x plus a y, and here is y. So what is the resulting vector? Important fact, the same y here. Yes? The same y is that you should put some line here, and the result is somewhere with the end of the same y. But not the same x. So in general, this is something like that. And if you think it over for all a's, you get all vectors here. So this is the picture of action of these matrices on general vector from R2. Now we want to find invariant subspace. Do you see some invariant subspace that which, again, invariant subspace is some line through the origin. Do you see some line which is preserved by all actions of all a's? Which should be the beginning vector in order that it is just multiplied. For example, this is not the case because after this matrix, it is in another subspace. But there is a subspace where it just leaves you in this subspace. Yes, it is this direction, yes. These are also vectors in this two-dimensional space, and leaving y unchanged means that you still are on the x-axis after acting of this group. Yes? So there is just one-dimensional subspace which is invariant. But it means that it cannot be this complementary subspace. We have a situation that because this is the only non-trivial subspace, one-dimensional, so complementary should be another one which is also invariant, but we see that it doesn't exist. So this is an example of representation which is reducible, but you cannot go further and find second invariant subspace such that these two together will create you the whole. And if this is possible, it is called completely reducible. Completely reducible, that it is reducible to a subspace that then you can find additional subspace, and so on. And you can write it as a sum of two invariant subspaces. So this is the case of reducible representation, but not completely reducible. Now they are very important for theorems, or lemmas actually, which are in this context, which were invented by Schur, German mathematician. Where it is? And we need one concept for it, and it is the concept of, so to speak, so-called intertwining operator. In Slovak splietajući. Intertwine is to splietać something. So a funny word. Sometimes you can find also equivariant. So what is it? In order to define it, you should have two representations of the same group. G, first in some first vector space, and second one in some second vector space, the same G. And now you should have this intertwining operator. It should be an operator from V1, some A, to V2, with this property that if you act in V1 by this first representation, and in V2 by the second representation, then this diagram closes with the same A. So if you write it by formulas this way, is that applied on element on V1, first row 1 G, and then this A, it should be row 2 G and A. First A and then row 2G. This is the definition of equivariant of mapping, and if it is linear mapping between two representations, it is usually called an intertwining operator. It also is expressed by words that it commutes with the two representations, but well, this is the definition of what does mean, that it commutes with the representations. It is important mapping that if you have some element from V1, first of all, our vector space is now richer. It is not only a vector space. It is vector space in which group G acts by some representation. It is called representation module sometimes. But module is a word which we will have it later on, and there is an appendix in my book, what is a module. So now I don't want to go to that, but it is more than a vector space. Yes? It is vector space with action of Lie group through some representation. Again, this is some other vector space, but more than just a vector space, because you can act by the same group by some other representation. So now linear operators between more than vector space 1 to more than vector space 2 can also have some very specific feature, and this is this very specific feature, that it, in this sense, commutes with the two representations. This formula, if you write it or act properly on some vector V1, says you that if you have something which transforms by group transforms the element V1 to another element V1. So you have a element from this which transforms with respect to group via this representation. Then if you map it here by this particular A, or A with this property, you obtain something from here which transforms by another representation. So it is this A makes you transformation of elements of type rho 1 that they transform as through rho 1 representation to elements of type rho 2 that they transform in the other vector space through V2 representation. So it is these are very important mappings. And what is the first observation, that you can have perhaps another operation with this operator with this property or mapping, some B. And then you can somehow add and so on these equations, and you will get that A plus lambda B the same. So if A and B are two intertwining operators, you can make a linear combination of those two guys, and it is still an intertwining operator. What does it mean? That, of course, linear mappings from V1 to V2 give you a vector space. We already know it. It was maybe on the first exercise on this. Do you remember that linear operators from V1 to V2 form a vector space? Vector space of linear operators from V1 to V2. But now we have a subspace. Not all linear operators from V1 to V2, but intertwining operators. They form a subspace in the vector space of all linear operators from V1 to V2. Yes, it comes easily from this. So there is a vector space of intertwining operators. It turns out that these operators are very important, very naturally somehow adapted to this situation. That was very important. And this is the reason why we want to find them. So the first observation is that if you want to find them, remember that they form a vector space. So if you want to find them, it is enough to find a basis in this vector space. Yes, because they form a vector space, finite dimensional vector space. So a basis is enough, not all of them literally. And there is a very important lemma, Schur's lemma, which is some statement which concerns these intertwining operators, but only for irreducible operators, representation. Some intertwining operators for irreducible representations. So something very specific holds for intertwining operators between these two irreducible representations, not more general. And maybe in order to this statement, I still have to introduce equivalent representation. What is equivalent representation? Well, two representations. In which situation we call them equivalent. When they are really equivalent. They preserve everything. That first of all, you should have the same dimension of this V. You should have some operator A from V1 to V2, which is linear isomorphism, from which it has, V1 and V2 have the same dimension. It's linear isomorphism, but it is not enough because there is an action of the group here and here. So it preserves the actions, and preserves the actions is exactly this equation. So what is it? It is in that they are equivalent if there exists an intertwining operator, which is at the same time isomorphism, linear isomorphism. Because in general, these two vector spaces can have different dimensions and so on. Yes? So now we need the same dimension, that means linear isomorphism, plus this property. Intertwining plus bijection. Yes? Linear. Then, if such A exists, the two representations are called equivalent. Now, let's use this isomorphism A to create a basis in V2. So we have some basis EA in V1, and we can introduce A of EA in V2 because it is an isomorphism. Then the matrices of row 1 acting on this EA give you matrices. Well, operators row 1 acting on basis gives you matrices, as usual. Row 1 G, A, B, E, B. Now, what about the matrices of the second representation in this properly chosen basis? So, row 2 G on this basis. Well, it is row 2 G, A, B by definition. But now, what is this? It is A image of this basis on the left-hand side. Yes. And this, it is some multiplication of two operators. From this, you can see that it is row 2A. It can be written as A row 1. Row 1 comes to original basis and produces row 1 G A B E B. Then this A comes by linearity directly on this E and produces curled E. Yes, by, where is here, the definition. A coming on E gives you curled E. So here it will be row 1 G A B curled B. Now if you compare this with this, you see something interesting. And what is the interesting fact? Just a small change, but very interesting. Which one? But not abstractly, but what? The matrices, yes? So the matrix of the first representation should be row 2, but by computation, but another computation, it is by definition, and by computation it turns out to be row 1. So this matrix is the same like this matrix. Yes? So then the concept of equivalence is clear, that equivalent representation in properly chosen bases have the same matrices. So of course they are equivalent because everything should be the same somehow in properly chosen bases. That if they don't look the same, it is your fault that you used bad bases. You should have some bases here and some bases here, and then everything is extremely simple. And the some basis here is just a image of any basis here. So this is the concept that sometimes you should take two representations as just one representation. They don't look like, but they are equivalent. In a sense, isomorphic. And it is important to understand this in order to understand what Schur lemma says. So Schur lemma says something like that, that imagine you have this situation for irreducible. This is very important. Then there is only two possibilities occur in general. That either row 1 and row 2 are equivalent, or A is 0. So what is the depth in it? That in general, if this and these are irreducible representations. First, they can have different dimension. For different dimension, they cannot be equivalent. So in this case, the only A which works here is just 0A. You can check that 0A always is okay. 0A is intertwining operator because intertwining operators form a vector space, so there should be some 0 operator there, yes? So we can check first that A equals 0 works. Then the statement here is that if they have the same dimension, only A equals 0 should be there. No other possibility. Then if they have the same dimension and they are equivalent, it is another possibility. It could be non-zero, it is isomorphism, and it is non-zero. So in general, operators between V1 and V2 of different dimensions should be 0, and if they are the same dimension, still there are a lot of operators between 0 and everything. It is something like everything or nothing, yes, here. This is nothing, this is everything, because it is completely equivalent. Yes? In general, there are operators also in between, but for irreducible representation, they are just these extreme cases, or everything or nothing, nothing between. Yes? This is the statement of this lemma. It is the first part. Well, I will just give a proof, because it is really funny that the proof is extremely simple, and the lemma is extremely strong, actually. It is the basis of many things working with representations of groups. On this lemma, a lot of other statements is based. So, first, this A has kernel and image. Kernel is, as is well known, a subspace of V1, and this is a subspace of V2. And it turns out, by very simple computation, that both these subspaces are invariant subspaces. So, for example, let V1 be from the kernel, yes, which is V1 is an element of capital V1, but of more specifically from the kernel. What does it mean? That A kills it, by definition. Now, we act, if it is invariant subspace, which we want to prove, it should be that if we act by row 1 any G on this V1, it should be also killed. Yes? if this is 0, this means that it is invariant subspace. Now, is it 0? We can convert this by rho 2 GA by the basic definition. And A kills V1, so it is 0. And you can prove by the same way that also this image is invariant subspace inside V2. Yes? And now, so it is easily checked that this is true. Now, we have not equivalent, but irreducible. But irreducibility of both representations says that, okay, we can have invariant subspaces, but only trivial. So this means that kernel of A is either complete V1 or 0. An image of A, the same story, V2 or 0. So there are two possibilities in V1, two possibilities of the other space, or altogether there are 4 possibilities. Yes? And check these 4 possibilities, what they say actually. For example, if image of A is 0, what does it mean? It is a 0 operator, yes, this A, yes. But it can be 0, yes. So it is one of possibilities. So check all 4 possibilities, it is completely trivial. And you will see that all these 4 possibilities say you exactly what is written here. Yes? So the proof is really very simple. And the second part of the lemma says that if our representations are some second part, this is first part. If rho 1, rho 2 irreducible and complex, it is important, representations. What is a complex representation? That you have complex vector spaces. That means that if you fix a basis, then you will have as operators complex matrices. So this as matrix will be n by n complex matrix. This will be important for the proof, and then there is a counterexample that if it is not complex, it is not true. Yes, so it should be complex. And then something like this happens, that if they are complex representations and equivalent, irreducible complex which are equivalent, then there is a freedom that if some A makes you this equivalence, this means this equivalence, or produces this equivalence by this definition, that any other equivalence is given by just a multiple of the first one. Yes? So this is the statement of the second. I will prove it next time, Wednesday. It is quite short. Not, well, like that. So there is just one-dimensional freedom in all this isomorphism which make you it equivalent. And it has a second consequence which is even more important. Actually, if you in physics read something that we use Schur lemma, it is still not this, but it is some consequence which will be next. That if something happens, your operator is multiple of unity, something like that. It is still just a preparation. But it also shows you that Schur lemma says something much more. And what is in physical textbook Schur lemma, it is some small part of the Schur lemma. Okay, thank you. It was already the end.